So as we said, this pi I being equal to 1 over the expected return time to I is actually a very nice computational help in the computation of this expected return time. So we basically compute this expected return time as 1 over pi I. That pi I can be computed from these equations, pi transpose pi equal to pi transpose and summation pi j equals 1. Of course, this may not always be easy because this involves solving a bunch of linear equations, a system of linear equations. But in the cases where we can actually guess a pi, guess a stationary distribution, you can just verify that that is indeed a stationary distribution, which might be easier. And that will in turn give you expected return time using this recipe. Now, on the other hand, there are situations where you don't really have to verify this equation entirely. And that situation is called, one of the examples of such a situation would be when the Markov chain is actually reversible. Okay? So what is reversible? So let me first start with that, and then I'll tell you how this is going to help in the computation of a stationary distribution. A Markov chain Xn is called reversible with respect to a probability distribution pi if pi I times pij equals pi j times pji. Now, why this name reversible? That would become clear from this exercise that tells you that if you have a reversible Markov chain, something that is reversible, a Markov chain that is reversible with respect to a probability distribution pi, and you start the Markov chain at the distribution pi, then for any positive integer n, the joint distribution of x0, x1 all the way up to xn is same as the joint distribution of xn, xn minus 1 all the way to x1. So in other words, you can reverse the Markov chain. You can run the Markov chain in the reverse time, and still the joint distribution of the Markov chain will remain the same as long as you start the Markov chain at pi. Okay, so this is why this is called reversible. Okay? The Markov chain is called reversible because you're basically reversing the time and the distribution is remaining unchanged. Now, how the reversibility helps in the computation of stationary distribution is because of this proposition. Okay? So if xn is reversible with respect to a probability distribution pi, then that probability distribution pi has to be a stationary distribution of xn. It may not be unique, but it will be at least a stationary distribution of xn. Now let's quickly prove it. The proof is actually very easy. So for each j in S, observe that if you take the sum of pi I with pij, okay, I runs over S, this would be just pi j times pji, right? Because of the reversibility. This is where I'm using the fact that this is reversible. Now, of course, this is a sum over I, so pi j can come out. You'll just have pi j times sum over pji. But this is P is a transition matrix, so therefore this has to be 1. This sum has to be 1. So therefore this is equal to pi j. And that shows that indeed pi is a stationary distribution. It's a 2-line proof, maybe 2-3-line proof. But the point is, once you check reversibility, you actually check that pi is a stationary distribution for the chain. In addition, if the chain happens to be reducible and positive recurrent, that will automatically tell you this is a unique stationary distribution. So therefore, this is a huge help in finding a stationary distribution. If you can find a probability distribution pi such that the Markov chain becomes reversible with respect to that probability distribution, then you have actually found a stationary distribution. This is a huge help in the computation. Now, one important corollary is that if you have a Markov chain on a finite state space, such that the transition probability matrix is symmetric, then uniform distribution on S is a stationary distribution for Xn. Now, this follows from the fact that if you have transition probability matrix is symmetric, then this will immediately imply that Xn is reversible with respect to the uniform distribution on S. And therefore, uniform distribution on S would be a stationary distribution. Now, here are two exercises. Show that you consider simple random walks on Zn and also the group Z2 power D. In both cases, you can check that the transition matrix, one-step transition matrix is actually symmetric. And therefore, uniform distribution would be a stationary distribution in both cases. So in the first case, the uniform distribution on Zn is a stationary distribution. In the second case, the uniform distribution of Z2 power D is a stationary distribution. Now we will actually show, and I think we'll do it in the next class, maybe the class after that, show that both of these are examples of positive recurrent and irreducible Markov chain. This irreducible is obvious, but positive recurrence is not. That we'll show that. So once we show the positive recurrence, it will follow that uniform distribution in that in the state space, either Zn or Z2 power D, whatever it is going to be the unique stationary distribution for this Markov chain. And one application would be on the on-off process. So recall the on-off process. We start with D lamps, all of which are switched off at the beginning. And then we choose one lamp at random and switch it on. Then we choose another lamp at random independently of the previous choice and the configuration of the lamps. And what we do is the chosen lamp, we just change the state of the lamp. So in other words, if the lamp was on, we switch it off. If the lamp was off, we switch it on. And we keep repeating these steps 2 and 3 independently. Okay. Now suppose tau is the number of steps needed for all lights to be switched off again. We started with all lights switched off. Tau is the time after which all lights will again be switched off. Now, we'll actually compute expected value of this tau. This with the main step would be to show that basically remember this is essentially a simple random walk on Z2 power D. So the main step would be to show that the simple random walk on Z2 power D is positive recurrent. And once it's positive recurrent, by the previous exercise that I gave you, the uniform distribution on Z2 power D would be the unique stationary distribution. And therefore, from there, we'll be able to compute the expected return time to the initial state. Okay? All states switched off. We'll solve this in details, but this, just one gap is there. We have to just show that this simple random walk on Z2 power D is positive recurrent. Once we show that, we'll be able to compute the expected value of expected return time to the initial state. Expected value of tau, that is. So this shows that this stationary distribution is helpful in also computation of expected return time. Okay? As long as the Markov chain is irreducible and positive recurrent. And one of the ways to achieve it would be through reversibility, which helps in finding a stationary distribution.